Here is my lecture, so my talk. So let me start. First of all, what am I want to talk about graph limit theory, some older results as an introduction, and then something about what we are trying to do these days. So the generic question is the following. Suppose you have a sequence of larger and larger finite structures, but not only are they larger and larger, they become more and more similar, at least in some sense. And then you would like to know whether for a late member of this sequence, there is some kind of template, whether you can say how they look like, whether you can imitate this sequence. Now let me have a plan. I describe you the plan of this talk. I will first talk about a bit of history. Then I will talk about two cases of graph limits, which are reasonably well understood. Not everything is solved, but they are reasonably well understood. Sequences of dense graphs and these limits that I mentioned. And then I would like to talk about the main question, which is what happens in between. What are the possible candidates for limit objects, and how far are we in proving this? And then I will talk about, give a few examples of why are we interested in graph limits? What is the use of this, other than it's a nice theory and there are some interesting techniques to prove things? What is the gain in working on this thing? So let me go back. Actually, an early construction of this nature I found is the construction of continuous geometries by John von Neumann in 1936. So he was interested in what can you say about the middle ranges of the dimension of a linear subspace of a linear space, if the dimension is very large, and if the dimension tends to infinity, then and you normalize the dimension appropriately, it turns out that you get this kind of continuous version where the dimension can be any real number between 0 and 1. With Erdős and Joel Spencer, we described some kind of limits of subgraph counts, or at least were interested in that. I will come back to this. This was some attempt, but much more has been obtained in that direction recently. Anders Björner in 1986 turned to von Neumann's work and generalized it to other matroids. In particular, he introduced continuous partition lattices. And then Anders Björner and I, the next year, introduced other interesting continuous matroids. Perhaps interesting. For example, continuous number fields, where the transcendence degree of the number field subfields can be arbitrary real number between 0 and 1. And a much more important development also in the 80s was introduced by Gromov, who introduced convergence to metric spaces. And this theory has interesting connections with ours, but I will not be able to explain and explore this. Graph limit theory has been developed during the first decade of this millennium. But some of it is much older. The scaling limits have been introduced in statistical physics. I will not talk about those. Benjamin and Schramm introduced limits for bounded degree graphs and also for planar graphs, which are only bounded degree on the average. And on the other end of the scale, for very dense graphs, so graphs with a constant times n² edges, Christian Borch, Jennifer Chase, Vera Turan-Sors, Balázs Szegedy, Kati Vesztergombi, and myself worked out the theory of their limits. And I should mention, but unfortunately I cannot talk about this, there is an interesting notion of first-order convergence of graphs which connects logic, formal logic to graph convergence theory, developed by Arik Nesetchil and Patrice Osson and Mendes. Now, there are also limit theories, and that's typically happened in the next years, limit theories for other mathematical structures. Limits of partially ordered sets was developed by Svante Jansson. Limits of permutations by Hoppen, Koayakava, Moreira, Rath, and Sampaio. Limits of functions on abelian groups is a very important topic. It was in this form introduced by Balázs Szegedy, but in a little bit different form of sort of approximate group theory was introduced by Green, Tau, and Ziegler. And this relates closely to the famous work of Semeredi on arithmetic progressions, develops it much farther. And for hypergraphs, in the dense case, Elek and Szegedy developed limit theory. So there are lots of similarities between these theories, but I will talk about graphs. So recall that I was saying let's look at a sequence of graphs which are becoming more and more similar. So what do we mean by more and more similar? Let's just look at a few examples. Complete graphs, for example. They are, of course, quite different if you look at small complete graphs, but if they are bigger and bigger, then they seem to be losing every feature except that they need to be that they are complete, that everything is connected to everything. Cycles. If you look at longer and longer cycles, this is starting to become tricky, because if you look at the way I drew these cycles, then it's natural that they are becoming more and more like a circle, more and more similar to a circle. And that's of course classical. That's of course classical geometry going back to Archimedes. But if you are sitting at a node of a cycle, then these cycles will become more and more similar in a different sense. This means if you look around, you will see a path going off very far in one direction and another path going off very far in the other direction. And as the size of the cycle goes to infinity, these paths will meet only very, very far. So basically, they are more and more similar in the sense that you don't really see the path meeting. So it seems that you are sitting in the middle of an infinite path. you can look at grids in the plane. And I have drawn the same sequence in two different ways. And in the first case, you would say that these grids tend to, well, to a square, which is a solid square. And indeed, this is the notion of scaling limit of these used in physics, in statistical physics. The second sequence, however, seems to indicate that you can also converge to a single infinite grid, which is still somewhat debatable, but I will come back to this in a minute. Anyway, more and more similar can have different meanings. Just to give you a fun example, we can look at Penrose tilings. These are tilings of the plane by two rhombi. And if you sort of require which edge of which rhombus can join to which edge of the other type or of the other rhombus, then they tie the plane, but the plane cannot be tied with them in any periodic manner. So there are these are non-periodic tilings of the whole plane. And if you take bigger and bigger pieces, then the theory of Penrose tilings tells you that they will be more and more difficult to distinguish, because whatever you find in one, if you go far enough, you will also find it in the other, whatever subgraph. And then a more mathematical example of a sequence which is becoming more and more similar is a sequence of random graphs, which say edge probability half, Erdős-Rényi random graphs, which is one of the interesting consequences of random graph theory, that these graphs are really becoming very, very similar. This is actually maybe an even bit more surprising if you think of an Erdős-Rényi random graph as on n nodes, as you draw every graph on n node on a piece of paper, you put all these papers in a bag and you pull randomly one out. Of course, every graph you can pull out, but whatever you pull out with large probabilities, so you pull out, if you pull out two of these, then it will be very difficult to distinguish, or if you do it for n and n plus 1, it will be very difficult to distinguish. So we would like to get a template for late members of this sequence. Oh, sorry. Happened. Yes. And so the question is, what does it mean mathematically? So more and more similar we have to define, so that leads to a notion of convergence. And the template for a large graph in this sequence corresponds to a construction of some kind of limit object of this sequence. So here is, the point is that limit objects are convergence notions fall into more or less two categories. Think of a very large graph G. And suppose you want to study it, to get information about it. And one possible notion is to try to map a small graph F into G and see what happens. For example, you map a triangle into G, and then you count how many ways you can map the triangle into G, or what is the probability that that the triangle, if mapped randomly into the node set of G, will actually preserve edges. Or you can go the other way and map G into small graphs. And these kind of properties, left and right properties, are all over the place. So counting subgraphs is what I told you. Closely related notion is neighborhood statistics. You pick a node of G, and then you sort of look at all points which are at a bounded distance from G, and then if the degrees are not too high, then you maybe explore this bounded distance neighborhood, and that gives you a statistics of these bounded degree neighborhoods. A special case of this is, which is extremely important all over graph theory, is degree distribution of G. So how many degrees, how many nodes of degree 1 and 2 and so on does it have? There is also eigenvalues. That's maybe a little bit less obvious, but if you are able to count cycles in graph, you know how many triangles, 4 cycles, 5 cycles, and so on are in this graph, then from this you can recover, from these numbers, you can recover the eigenvalues of G. The other side is also quite important. A model in statistical physics corresponds to mapping G into the set of possible states. So in statistical physics, G is like, say, the graph of atoms of some piece of crystal, and H is the set of possible states in which these atoms can be. So in the Ising model, this is up or down, just a 2-element set, and then you map it there, and then the partition function of this model and so on, important statistical physical quantities arise by counting these kind of mappings. The chromatic polynomial, favorite classical notion in graph theory, is the number of maps of G into edge-preserving maps of G into a complete graph on Q nodes. That's the value of the chromatic polynomial at Q. And then you can also encode the maximum cut by mapping G into a graph with 2 nodes and then counting the number of edges which are mapped onto going across. Regularity partitions or semi-radial partitions, and as opposed to eigenvalues, eigenvectors are on this side because you map G into real numbers in that case, not finite graph. So studying a graph from left to right is all over the place, and so you can define use it to define convergence. Now, let me introduce just some graphic way of explaining the basic idea. So here is a graph. It's drawn in the usual standard form. If the graph is very large, then this kind of drawing becomes not very useful. You don't see much. Here is the adjacency matrix. Probably you see even less than on that graph, but but you can improve it a little bit by replacing the zeros by white squares and the ones by black squares, and then you get this kind of picture which looks like a crossword puzzle, and so this way you make the graph maybe visual in another form, not the standard way. So for example, here is this kind of picture of a random graph with edge density half, so half of the edges are present. There are 100 nodes and about 2,500 edges. Now, if you increase the number of nodes, then obviously this picture becomes more and more similar to a gray square. Here is another example. This is a graph it's also randomly constructed graph. This has 200 nodes. I will not describe you the procedure which constructs this graph. It's not really important. You can come up with all sorts of easy recursive ways of constructing graphs which are not homogeneous. But what you can observe is that this picture is very similar to the picture on the right, which is just a grayscale image of the function 1 minus the maximum of x and y. Probably many of you have seen these couple of last slides. My goal was to motivate why we look at graphons as limit objects. So these are these grayscale images that we obtain when the number of nodes goes to infinity. And a graphon is just a symmetric measurable function defined on the unit square with values between 0 and 1. And graphons serve as important limit objects, but to understand in what sense they are limit objects, or consider them as generalized graphs, you have to extend a lot of graph theory to graphons. That's not always straightforward, and there's been a lot of work on that, extending connectivity properties, matching spectra, automorphisms, and so on. So graphons are limit objects. So in what sense? They are limit objects for dense graphs, and they are in the left convergence sense, certainly. That's how it is easiest to define. The density of a graph F in G, that's a definition, is the probability that a random map from the vertex set of F into the vertex set of G preserves edges. So this is a quantity, TFG, which is the number of edge-preserving maps, homomorphisms from F to G, divided by the total number of maps from F to G. And so this is a number between 0 and 1, which we call the density of F in G. And now here is the definition. A sequence of graphs is left convergence. These are dense graphs. If this sequence of densities is convergent, we fix F and we compute this density of F in each of the members of the sequence. And if this is a numerically convergent sequence for every F, then we say that this sequence of G's is left convergent. Now, getting to the limit objects, we need to appropriately extend this notion to graphons. And here is this integral which can be used for that. It is maybe late in the day. It's a simple integral, but I will not go into the details of that. It's easy to compute for every F. And we say that a graph sequence of graphs Gn converges to the graph W, the graphon W, if the density of F in Gn converges to this integral density of F in W. So, for example, an Erdős-Rényi random graph, as mentioned before, converges to a gray square, which corresponds to the grayscale representation of a graphon, which is identically a half as a function. And let me go through very quickly the main facts about this definition. First of all, if the sequence is convergent, so these numbers T, F, G, N form a convergent sequence, then the limit can be represented by a graphon. So every sequence, a convergent sequence of graphs, left convergent sequence of graphs, has a limiting graphon. Now this graphon, you may wonder, actually, everybody wonders first that this is a very general construction. It's a just measurable and symmetric function. So there are lots of them. You would think that maybe a graph sequence would converge to something more decent, maybe a piecewise linear function, maybe a continuous function. I mean, after all these graphs are finite. But the second statement says that for every graphon, there is a graph sequence converging to that graphon. So, well, okay, maybe, but maybe still for every convergent graph sequence, there is some very simple graphon, maybe a piecewise linear graphon, and there is also another one. But that cannot happen either, because the limit graphon is essentially unique. Essentially has to be explained as up to measure preserving transformations and changes of measure 0. Now, this is also probably you have heard this many times, but let me point out an important fact about the second statement here. If you have a limit theory and you have a conjectured limit object, you can ask whether there is any sequence that converges to it. So, and here we know that for every graphon there is such a sequence. And that's called in group theory sophicity. So a countable group is sophic if you can approximate it in some sense by finite groups. And it turns out that for graphons, this is an important and nice property. What about right convergence? Well, right convergence starts with mapping G into some finite small set, small meaning compared with the size of G, and fixing the size. So what you can do then, and more or less that's all that you can do, is count how many edges are there. So suppose here in this picture, G is mapped onto these 3 nodes, and then there are maybe 256 edges that are mapped onto the loop on the top, and maybe 149 edges are mapped on the pair, and so on. So this is a weighted directed complete graph, also allowing loops, which I will denote by G/P. And then we can look at the set of all such graphs, weighted graph G/P, which is where P is a partition into a fixed number Q of classes. I denote this by capital Q sub Q of G. This has to be normalized, which I will now ignore. But if it's appropriately normalized, then you can prove that left convergent sequence is also right convergence in the sense that these associated sets, these associated sets of weighted directed graphs is convergent in a Hausdorff distance. This is a subset of Q squared plus Q dimensional real space, and these subsets are convergent in Hausdorff distance. I just wanted to mention to point out that there is a nice equivalence here between some notions of right convergence and the very natural notion of left convergence. For bounded degree graphs, I will just spend very little time. Here, you again can count the number of homomorphisms from a graph F into the graph, the members of the sequence. but you normalize differently. Instead of normalizing by the total number of maps, you normalize by the size of by number of nodes in GN. And if this converges for every connected F, again, connectivity is a technical condition to impose here. So if this converges, then this sequence is locally convergent. And there are limit objects for this convergence. These are called involution invariant distributions on countable rooted graphs. They were introduced by Benjamin and Schramm. I have to mention that they give a different definition, but it's an equivalent definition of convergence. I just wanted to make the definition more similar to the dense case. So the point I would like to make with this is that the key to defining convergence in both cases is that we can count number of homomorphisms from F to Gn. And another remark about sophicity, it's a famous unsolved problem for this case, whether every such limit object, so it's a probability distribution on countable rooted graphs, of course, also with the same bounded degree, which has some involution invariance property, which I will not define. The point is that this is closely related to Gromov's problem that every countable group is Sophic. In fact, it would imply that every countable group is Sophic. So this is an absolutely fundamental question in this bounded degree case. There is another limit object one can define here, and that will be closer to the way I would like to further develop the story. And that's a graphing. The graphing is a Borel graph on the unit interval, say, with bounded degree. Borel graph means that the set of edges is a Borel subset of the unit square. And there is some kind of condition which basically says that you can double count in some sense, counting edges from A, but it is not sum, but it's integral, but it expresses the same thing. At least in the finite case, it's equivalent to just here is a way of thinking of these graphings. They are here is the unit square, and then there is an essentially one-dimensional set of edges. It turns out that an example is if you just take any collection of segments with slope 45 degrees or negative 45 degrees, you have to make it symmetric. So if you look at the node on this edge, which is a set of nodes, so you look at that point here and go along the corresponding, then it will you the edge. So that is interbounded now. Again, the implies problem that you have to extend graphs to graphing, either along some of it area of algorithmic stuff has been extended to graphings or to the Benjamin-Schramm version of the limit. Now I come to lots of people but every other property generalizes, find an infinite mean unit.
We were having some difficulties in hearing Professor Lovász. Okay, how are we doing now, Professor Lovász?
I was disconnected. Okay. Can you hear me now?
Now we, I guess the IT support reset the whole thing. So I think.
Yeah, I am sorry, but that's
okay. So
seems to happen with.
Share your screen.
Okay, I will share my screen here. So, can you see my screen now?
Yes, we
okay.
can see your screen.
Okay, so I'll try to continue. Sorry about that. So to being able to pick a random node implies that you need either a finite or a continuum node set, because there is no uniform distribution on a countable set, one of the set facts of probability theory. So, so you have a symmetric probability measure on the square. And recalling the previous examples, a graphon would be a symmetric probability measure on the square, which is absolutely continuous with respect to the uniform measure. And the graphing would be here on the right, a very singular measure on the unit square, concentrated on an essentially one-dimensional set. But there are all sorts of other intermediate cases, and here is a nice one. You take the unit sphere, and now you can define, well, you could define a graph on it by connecting two nodes if they are at rectangles at 90 degrees. But then all these pairs look alike, so there is a uniform measure on that, on pairs. On orthogonal pairs. And and this uniform measure gives an example. Okay, you say that I defined it as a measure on the square of 0, 1, and here you have the measure on the square of the unit sphere, but they are all alike from a probability point of view. You could measure map the unit sphere into the unit interval in a measure preserving way. And this is an interesting object, which turns out to be a limit. Okay, now I will define. So I believe that a good notion of limit objects in these intermediate cases is a Markov space, which is just a Borel sigma algebra endowed with a symmetric probability measure, whose two marginals are equal. Well, if it's symmetric, if not symmetric, you have to add that the two marginals are equal. And these marginals are called the stationary distribution. And if you, in the finite case, this defines, as it's well known, it's proportional to the degrees of the points. This is really every Markov space is just equivalent to a reversible Markov chain with a stationary distribution. And then it defines an ergodic measure eta. And why? So this is equivalent. So we are in mainstream probability theory with this choice of limit objects. And you may have to add, let me skip this, you may have to add a separate node measure to this, which may or may not be absolutely continuous with respect to the stationary measure. And then you can extend graph theory to Markov spaces. And in fact, a lot can be flows, expansions, spectra, random walks, and a number of other notions can be defined for Markov spaces. I will skip this. Flow theory can be extended in a very nice way, but I would rather talk about my last, what are graph limits good for? There is an easy answer, which is about existence of optima. So this is, again, something I often show that in classical or first year calculus, you get a problem like minimize x cubed minus 6x over non-negative values of x. And of course, the optimum is at square root of 2, the minimum. And so the minimum is not a rational number. And that's why real numbers are useful, because among rational numbers, this problem has no solution or only approximate solutions. But if you extend it to real numbers, then it does have a solution. And on the other hand, you can ask a graph theory question. Let's minimize the density of 4 cycles in a graph, fixing the edge density to be 1/2. And there is an elementary theorem, I think, going back to Erdős, which says that this density is at least 1/16, actually strictly larger than 1/16, but it gets arbitrarily close to 1/16 for random graphs. So here is a graph theoretic extremal problem, which does not have an optimum, because it's always strictly larger than the infimum. But so that's why graph limits are useful, because extending, you get the identically 1/2 graphon, which we have met before. And so the minimum is attained for this graphon. Now this interesting fact, it says that just by saying that the edge density is 1/2 and the 4 cycle density is 1/16, this graphon is uniquely determined. So the question, are there other examples of this? So let's call a graphon W finitely forcible. If there is a finite list of graphs, Fi and real numbers alpha, so that if you fix these densities, you require that W satisfies these equations, then there's a unique solution W up to measure 0 and so on. So my introductory example was that the constant 1/2 function is finitely forcible, and actually every constant function is finitely forcible by requiring that the edge density is P, the 4 cycle density is P to the 4th. Complete bipartite graphs are finitely forcible. That's by, again, classical extremal graph theory. If a graph has edge density 1/2 and triangle density 0, so it contains no triangles, then the only possibility is that it's a complete bipartite graph. and so it's uniquely determined. These examples suggest that finitely forcible graphons are essentially templates for optimal graphs in extremal graph theory. This is not completely true, but it's approximately true. Now, what are finitely forcible graphons? Step functions. We proved with Vera-Schorsch that all step functions are finitely forcible. And of course, we conjectured that these are all. It's a natural conjecture at this point. But then a few years later, Balázs Szegedi and I found a large variety of further examples. Nevertheless, we were able to prove that there are many more graphons that are not finitely forcible, because finitely forcible graphs form a set of Baire category 1 in the space of all graphons. Whereas this is a complete metric space, so it's a category 2. And if you are interested in explicit examples, the functions x plus y over 2 or x times y, these are very decent graphons, and they are not finitely forcible. Now, we formulated several conjectures about finitely forcible graphons, mostly trying to get the following chain of implications. If you have a graph which is an extremal graph, so a solution of some extremal graph problem, then this is finitely forcible, motivated by the Turan and many, many other examples. And then this has nice properties, of which maybe the most relevant for extremal graph theory would be that they have polynomial size semi-ready partitions. So these were several conjectures. They looked very difficult. And then all of them were disproved. But this is usually a sad thing, but let me show you that even though they are all disproved, the way they are disproved raises extremely interesting novel problems and constructions. And let me show you this. And this was done by Daniel Kral and his younger students and postdocs and collaborators over last 7 years or so. And they are extremely interesting constructions. So let me show you only one, what I find the most interesting. So let's start with a graphon. And this looks like a cat, but actually this is a graphon. It's a symmetric, it's a grayscale image of a symmetric function. Now, what they prove is that you can embed this graphon, you can add something around it so that it becomes finitely forcible. And not only finitely forcible, it can be forced by something like 100 graphs, a fixed set of 100 graphs whose density you prescribe. So it means that if I am interested in encoding this picture on the left, then it suffices to specify those 100 densities for fixed graphs. So to encode this picture into 100 real numbers so that it uniquely determines this picture by finding this finitely forcible graphon, throwing away 3/4 of it, and keeping this 1/4, which is the original picture. There is, of course, there is an issue about ordering the rows and so on, but this is an amazing consequence, and I think it might have very many further applications, and it might inspire a lot of further thoughts. So let me finish my talk with this beautiful example.